we have two random variables, x and y, i.i.d. exponential, and then t is the sum of x plus y. Here, t can be interpreted as, so as x is the waiting time, so for an event to happen in continuous space, t is the sum of two processes and their waiting time. That's how we can interpret the random variable t here. So in the first part of this question, we're asked to find the conditional CDF of t given x. And so that is, the PDF is the probability that x is less than or equal to a little t conditional on knowing x. And here we can start by recognizing that t is the sum of x and y, and so that is helpful because we can now set little x, so little x here. So we already know x, so it means that we can write this part as little x instead. Okay, so let's do that. So let's just remove this, and so this is now a fixed number. So that is helpful, and now we write this as y less than t minus x conditional on, like so. And y and x are independent, so we can drop the conditioning. We're left with y t minus x, and that is, now plugging in, we know the distribution of y, which is exponential, and that is 1 minus e to the lambda t minus x. And this is valid for values where x is less than t. Otherwise, this probability is 0, and we can recognize that by looking at this inner term in the parentheses, or seeing that x is indeed the sum of x and y has to be less than t. So and this condition basically that this has to be this has to always be larger than 0. So we can derive this condition in several ways. Okay. So now in question B, we're asked to find the conditional PDF and verify that it's a valid PDF. And now we just calculated the CDF, so the PDF of t conditional on x is the same thing as the derivative with respect to t of this term here, respecting the conditions that we have derived. And so this is the same thing as e minus lambda t minus x. And now this we multiply by minus lambda. So, and we have a minus there, so we have a lambda term like so. And now we're asked to check whether this is a valid PDF. And that we do. So the valid PDF should sum to 1. So we ask if this integral, integrating this PDF that we have here, going from, and so where do we go? Where do we start? We start from x, so t we're integrating because we're integrating on t space, x up to plus infinity. And this we can just exchange. So we have dt, right? And if we set now, say y, or anything, let's just set z, for example, z, which is just a dummy variable, t minus x, and so just doing a subtract, d as dt, so this whole thing can be written as duplicate, we change this to y, this to z, and z, and now the new limit of z, so t, as t goes to infinity, z goes to infinity, so that's correct. And when t goes to x, this term x minus x is 0, so we change this limit to 0. And this we recognize being the exponential, the regular exponential, the standardized exponential, which we know sum to 1. So this is indeed a valid PDF that we have found here. All right. And now moving on to the third part of this question. We asked to find the conditional PDF of x on t and then verify that this is a valid PDF. Okay, so let's do that. And here we start by writing out f of x condition on t. So let's see, actually we should start with probably easier to start with the CDF. Let me just validate this with my notes to see what we can do here. Well, actually we know that we can proceed based on the PDFs, because we know we have derived several of those PDFs already. So this, using base rule for continuous cases, we'll just write this as f of t, and now we write this as f of x and t, and so we write as f of t, then use the following conditioning, which is always true, is just a reformulation on little t, f of t. For symmetry, I'm just going to write this. Sorry, this is wrong. We don't want to condition on that term. We want to condition on the other way. So we condition on x, because that is what we know. Like that. Okay. That's good. And we can, we could try to sort of brute force calculate all these PDFs, but so we know, and just say that this we know already from the from what we've calculated in the other exercise. I'm going to write this like just to clarify what we're going to do here. So this we don't know, so the PDF of t, but we know the PDF of the conditional PDF of t conditioned on x that we derived just here. Copy this. Oops. Don't want to cut it. I want to copy it. Let's move it here. Paste. I'm going to remove this. And we know what the exponential is. The PDF of the exponential minus lambda x. Okay, but we don't know what the PDF of t is. So this seems to be tricky. So we can just try to derive that, or we use a little trick, which is that we know that all PDFs have to sum to 1, right? So we then write basically this as a sort of a this is a normalizing constant in this conditioning. So what we're going to do is that we're going to say that for this to be a valid PDF, it has to sum to 1. Over its support. So over its support x conditioned on t. X, let's just write x conditioned on t, like so. Okay, and so this and this is the same thing as going from, and we know that x has to go from 0 to t. That's what we reasoned about in the earlier parts of this question. And we know that we're just going to write this whole thing here. Well, we could say I'm jumping around a little bit here. So what we want to do is that we're going to take this piece, and that's what we are integrating over, and we're going to basically say, so this is a constant that will not depend on x. So we can write it as, let's just write it as a c. It's a constant. Copying it here. Duplicate, like so. dx. Now we can multiply out the c. We can multiply out the c so that we have basically 1 times c. So I'm basically taking it out and putting it here, and then what is remaining is this term here, obviously, then removing this. And so what we're left with is lambda 2 integral 0 to t e to minus lambda. Let's see, so we have minus lambda. We're going to add, well, let's just make this a little easier by first multiplying out this parentheses and then putting it together again. So we have plus x minus lambda x, right? And just basically opening up this parentheses. Let's just see, verify minus, yeah, plus, yeah, and then there's a minus here. And so this whole thing is, yeah, so we see that the x's cancel here. We're just left with minus lambda t. Okay, and that's a integral we know how to do. 2, which is e to the minus lambda t divided by lambda, like so, over 0 to t. Okay. Now we have actually clashing dummies, but bear with me, assume that this is just, this is, we can call it whatever we want, but we are integrating over the X region. And actually I see that I did one mistake here, which is that I have, we're supposed to obviously integrate over the X region. I just integrated over the D region, so that's clearly wrong. So let me do this from again. Sorry about this. So let's remove that. We have dx here. Let's think about this clearly and carefully. Yeah, so essentially what is left is this exponential that doesn't depend on x. So this is just a constant. So what we have is we can pull this whole thing out, e to the t, e minus lambda t, and then we have x going from 0 to t. That's what we have, and that is just t, lambda t e to the minus lambda t. Okay, and so basically the normalizing constant is basically this c here. Now I realize that I have let's see, let me just check some stuff here, which is that we have the f of t. Just checking that this is correct. Might have made a small mistake here in terms of switching certain things around. Yeah, so this is correct indeed. This is the normalizing constant, and so we have essentially found, verified that that C is a valid PDF. And in question D, I've actually already done it, sort of indirectly or directly, that the marginal PDF of is this, which is actually what the normalizing constant in this case is. So yeah.